In question 6, we're looking at a reaction rate law of this decomposition of NO2. And if I kind of look, I know I'm given some graphs that we're going to try to interpret, but if I look at the rate law that's given to me in the question, it says that rate equals K, concentration of NO2 squared. So the squared means this is a second order reaction. And so just as a little recap, this is the impact that this reactant has on the rate of reaction when I increase its concentration. So if I increase the amount of NO2, this will have a big impact on rate. It'll actually quadruple the rate. So in terms of these graphs, I guess the most simple kind of graph is just a regular, I'll just draw it here for a second, a regular concentration over time graph. So in terms of a second order reaction, it'll always be some sort of exponential decay. If I look at concentration of the reactant over time, what I see is that, yeah, it'll decay something like this, where if I have a lot of the reactant, it'll, the time of reaction will be very quick, okay? Because again, this is squared, so it will react quickly. If I don't have a high concentration of that reactant, the time of reaction will take a little longer. And it'll follow this kind of exponential pattern. And so we see the same pattern here when we take the ln of the concentration of NO2, the natural log of that concentration versus time. And then when we do 1 over the concentration of NO2 versus time, this will follow a linear pattern. That is true for a second order reaction. And it follows the linear equation y equals mx plus b, where the y is your 1 over NO2. That's your y-axis. The m is the slope. Now, in this graph, the slope, for example, if we do the slope from here to here, this rise over run, that's actually your k value, your rate constant. And then x is your time. And then plus b is over here, that's your y-intercept. And we say that that's 1 over the concentration of NO2, but initial. So I'll say NO2 naught. And so this integrated rate law, 1 over NO2, is kind of derived from, it's derived, or I believe integrated. But when you have these patterns, so this exponential decay for NO2 versus time, same thing for the natural log of NO2 versus time, and then this linear pattern for the 1 over concentration of NO2 versus time, this is characteristic of a second order reaction. So you may want to study the characteristic graphs of a first order reaction as well as a zero order reaction to help you just kind of review how graphs relate to your rate law. All right, so this is second order because this 1 over NO2 versus time graph shows a linear positive slope. Okay, which is characteristic of that second order. All right, the next one is talking about, it's a mole ratio question, the next one, because it says here the rate of disappearance of NO2 is determined to be 6.52 times 10 to the negative 7 mole seconds per liter, or capital M per second. Determine the rate of appearance in M over seconds of O2 at the same point in the reaction. Okay, so this is a mole ratio. You take the rate that's given, 6.52 times 10 to the negative 7. I'm just going to change this to moles per liter for a second so I can do my unit cancellation properly. So it's moles per liter per seconds. So I believe this is right. It becomes mole seconds per liter of, by the way, NO2. And when I do my mole ratio, remember, you want to put the units you don't want on the bottom, on the denominator. And in this case, I don't want moles of NO2. I want this to cancel out. I do want moles of O2. So I'll put that on the numerator. And then if you go back up to the equation, use your mole ratio here. So for every 1 mole of O2, 2 moles of NO2 were used. And so mole cancels out with mole. So my rate will be expressed to 3 sig digs, 3.26 times 10 to the negative 7 moles of O2 seconds per liter, which I'll just change the unit. So this is the same thing as 3.26 times 10 to the negative 7, capital M O2 per liter, sorry, per second. Okay, that's how we do question B. Question C is a Lewis dot diagram question, and there's different ways you can do this, but I like to use a method called the electron bank. So I'm going to show you how it works below, and then I know this one's already done. So this is the NO2, and what they want us to do is, it says that the NO2 nitrogen dioxide can be oxidized, so it can lose an electron to form NO2 plus. They want us to do the Lewis dot diagram for NO2 plus. So before we do that, let's just show this method I like called valence electron bank. So the electron bank, you want to empty the bank. So for example, in this compound NO2, nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, but there's 2 oxygen. So altogether there's 12. So you add these up, and I have a total of 17 valence electrons. And when you empty the bank, you empty the bonds first. So remember that each bond, each line is 2 electrons. So there's 3 bonds. So I'm actually going to empty 6 valence electrons here, leaving me with 11. Now, when you've maximized your bonds, you're going to empty the rest of your electrons as lone pairs or lone electrons circling the atoms. So for the oxygen on the left, I have 1, 2, 3, 4. 5, that's on the nitrogen, 6, 7, 8, 9, 10, 11. So I've emptied those 11 valence electrons, I've emptied the bank, and I've fulfilled my Lewis dot diagram. By the way, you can also use the formal charge check to verify that that's the best resonance structure, okay? So going on to my NO2 plus, remember, the plus means it got oxidized, so you lose an electron. So for nitrogen, I'm going to say we have 4 electrons now, 4 valence electrons. And oxygen, it's 6 times 2, so still 12. Okay, so in this structure, I have 16 valence electrons. I'm going to start by putting bonds in first. So I'm going to copy what I see here. So this is 2 bonds. Now on the right side between N and O, I'm doing a little mental math. This actually has to be a double bond for this to work out. Okay, you're gonna see why in a second. So by putting 4 bonds there, 2 double bonds, I've emptied 8 valence electrons. So I'm left with 8 valence electrons left. And I'm gonna empty those on lone pairs. Now this time, nitrogen will not get any lone electrons because it already has an octet. It has 8 electrons around it now, so it should be stable. So we're going to put these remaining lone pairs on the oxygen. Oh, sorry. Let me just draw this a little cleaner. And then put 2 lone pairs on each oxygen. So 2, 4, 6, 8. We subtract 8 valence electrons. We have 0. We've emptied the bank. And if you look at the structure, oxygen is an octet, so it's stable. That means there's 8 valence electrons around it, and nitrogen is also an octet. Okay, so we've completed the answer for the Lewis dot diagram. So let's do the last question. A student makes the claim that the bond angles in NO2 and NO2 plus are different from each other. This is VSEPR theory, okay? Remember VSEPR, valence shell electron pair repulsion. Do you agree or disagree with this statement? So there's a couple of answers on the answer key, but I like to use VSEPR theory. This is true. So we agree with this statement that these bond angles will differ. Now, my explanation has to do with the presence of lone pairs on your central atom. So in my NO2 plus, the nitrogen, there are no lone pairs on the nitrogen, on the central atom. So what that means is that where you see the oxygens, those electrons will repel each other to the maximal distance, which is actually a 180-degree angle or linear. So no lone pairs on the central nitrogen means that my NO2 plus will be linear and have a bond angle of 180. Now, the NO2 has a lone electron on nitrogen. So what's going to happen is this lone electron is going to want to repel these side valence electrons on oxygen. It's going to want to repel that down or repel that away. And this NO2 is going to have more of a bent structure. So we're going to say lone electron on nitrogen atom repels electrons on oxygen away, creating a bent VSEPR shape. Hopefully that makes sense, and you can watch the next video for the next question. Thanks.